So what is the first step if we want to do the Bode plot? What should we do? Maybe we should start by preparing the transfer function in the format we need for our Bode plot. How would this function read? Well, we want S divided by the cutoff frequency of each pole and 0 plus 1. So to do that, we need to factor out 0.1, 10, and 100. The top is fine because we have S plus 1. Right? So we could write this transfer function as g of S equals to S plus 1 to the power of 3. Then factor out 0.1, factor out 10, and factor out 100. And then you have S divided by 0.1 plus 1, S divided by 10 plus 1, and S divided by 100 plus 1. From the 0, for the 0 part, we don't need to do that because the 0 is already divided by plus 1. But if we had, let's say, S plus A here, what would go, how would we factor that out? If you had S plus A, we would want S divided by A plus 1. So we would have to multiply the function by so we want this to read as S over A plus 1. So we are factoring out A. A goes here. Multiply that back. It goes in. But don't forget that it has a power of 3. Because the whole thing is to the power of 3. Right? So if we had A, you would have to write it that way. Don't forget the power of 3 that comes from that. Right? For each of them, we are taking out one A. So there are 3 of them, A to the power of 3. Does that make sense? Yep. Okay. So now that we have all the poles and zeros in the format we want, we can find the gain of the transfer function, the DC gain, or the gain that we just factored out there. And we have 0.1 times 10, that's 1. 1 over 100, that is 0.01 S plus 1 to the power of 3, all divided by S over 0.1 plus 1, S over 10 plus 1, and S over 100 plus 1. Are we good so far? Yeah. So what do we have here? We have 3 poles. We have 3 poles and we have 3 zeros. The cutoff frequencies are 1, 0.1, 10, and 100. So let's write them down here. We have the 0.1, which is right there. 1 second. 0.1 is here. Then we have 1, 10, and 100. Okay. All right. So let's start by looking at the very low frequencies before we encounter any pole or zero. The only thing acting on the Bode plot at that level of low frequencies before our first cutoff frequency, which is 0.1 radians per second, is the gain. It's only 0.01. There are no poles at the origin. There are no zeros at the origin. If we had simply poles and zeros without a gain, the gain would be 0. I would start at 0. But here we have 0.01. So where does the Bode plot start? At very low frequencies, at 10 to the power of -3. Where does the Bode plot, what is the magnitude? Where does the Bode plot start? at 20 log of 0.01. Which is the same as 20 log of, what is 0.01? 10 to the power of negative 2, which is the same as 20 log of, sorry, negative 2 times 20 log of 10, and log of 10 is 1, so this is negative 40 dB. So the Bode plot starts at negative 40. Is it clear why it starts at negative 40 at 10 to the power of negative 3 radians per second? Yeah? Is it clear at home why it starts there? Okay, well, if I don't hear anything, I'll keep going. So it starts at negative 40. And we will stay at negative 40 up to the first cutoff frequency. And the first cutoff frequency we have is a pole. And it is the pole at 10 to the power of negative 1. The first pole s divided by 0.1. What happens to the Bode plot now? If this is a pole, what should we see? It should start going down by 20 decibels per decade because that's a pole. The pole adds negative 20 decibels per decade to the current slope of 0. So now we have a slope going down of negative 20. If at 10 to the power of negative 1, we are at negative 40 dB, what is the magnitude at 1 radians per second? 10 times the frequency from now. Negative 60. So the Bode plot is going down by negative 20 decibels per decade. We are at 0.1. If you travel to 1 radians per second, that is 1 decade, it has to go down by 20 decibels. So it goes down to negative 60. Because now the slope of the Bode plot is negative 20 dB per frequency decade. So why is not negative 20 log? The magnitude is always plus 20 log of something. Right? Magnitude is defined as 20 log of whatever we are measuring. The negative 20 log probably comes from the complex pole at the cutoff frequency. Maybe that's where the confusion is. Okay, so that's negative 60. What happens now? What happens now? At 1 radians per second, we are passing by a 0. Well, by 3 zeros, because it's to the power of 3. So at this cutoff frequency here, we have 3 times a 0. What happens to the slope of the Bode plot? Is 40 dB going up? Is it true? Yeah. Why? Because now each 0 that we encountered will add plus 20 decibels per decade to the Bode plot. We have a current slope of negative 20. We are adding 60. So we end up with plus 40 dB per decade. So now the slope is going to go back up at 40 dB per decade. Negative 20 plus 60. Why 60? 20 for each 0. So if now we are at now that we are at 1 radians per second, we're going to go to 10 radians per second. That's our next cutoff frequency. What is the magnitude at 10? Negative 20. Very good. So we go up to negative 20. And why is that? Because now the Bode plot once again has a slope of plus 40 dB per decade. And we land at negative 20, 1 decade from now. Now negative 60 plus 40. Yeah? All right. So the reason I stopped at 10 is that we have another cutoff frequency here at 10 radians per second. And this cutoff frequency comes from another pole. So what happens now? We're encountering a pole. We're going up on a slope of 40 decibels per decade. But we pass by a pole at 10 radians per second. That pole adds negative 20 decibels per decade to the current slope. It does not make the slope negative 20. It adds negative 20. We have a slope of 40. 40 minus 20 is plus 20 decibels per decade. So the slope changes to plus 20 decibels per decade, which means that 1 decade from now, we should be 20 decibels higher than we are at 10. So at 100, which is 10 times our frequency of 10, we should go to 0 decibel. So this is plus 20 dB per decade. And what happens now? At 100, there's another pole. What happens to the slope? The pole adds negative 20 dB per decade. The slope becomes horizontal, becomes 0. And we will stay at 0 dB per decade as the frequency now tends to infinity. And the magnitude turns out to be 0. Okay, so this is an approximation. If you plot this with Matlab, this is not going to, very likely not going to go down to negative 60. It's going to be like a smooth curve, not touching 60. It's going to go back up, but it should follow this more or less. If you want to use Matlab for that purpose, you can use the command Bode G, and it will plot Bode plot for you. Okay. Are we good? Any questions? Yeah. Yes. So yeah. So when we are at 10 radians per second, the slope becomes plus 20 dB per decade. Are we good there? Yeah. And then we are increasing the frequency, and we pass by 100. That's 10 to the power of 2. At that point, there is another pole. All right, there's this pole right here. And this pole adds negative 20 decibels per decade to the current slope. It doesn't make the slope negative 20. It adds negative 20 to whatever we have. We have plus 20, minus 20 becomes 0. So the line becomes now flat. And it will stay flat as time goes to infinity. Yeah. Any other questions? No? All right, let's do the phase. Where does the phase start? At very low frequencies, no poles at the origin, no zeros at the origin. The phase is? If there are no poles at the origin, no zeros, 0. Phase starts at 0. So the phase starts at 0, and the first cutoff frequency, it will change. And the first cutoff frequency is due to a pole that adds negative 90 degrees to the phase. So the phase goes down by 90 degrees. And we will stay at negative 90 degrees up to the next cutoff frequency. The next cutoff frequency is 1, 10 to the power of 0. That's the cutoff frequency of 3 zeros. So what happens to the phase? It goes up to 180. Why is that? Because each 0 adds 90 degrees to the phase. We have 3 zeros. We are adding 270 degrees to the phase. So we are at negative 90. Each 0 adds 90 degrees. So here's 1, here's another one, Here's another one. And we go up to 180 now. And we'll remain at 180 so long as we don't encounter another pole or zero. So let's continue to increase the frequency. We have another pole at 10. This pole adds -90. So the phase goes down to 90. And we keep going. We encounter another pole at 100, which adds another -90 degrees. So it goes down to 0. This is the rough estimate. So now we have to interpolate our values here. And we're going to do that as best we can here. And let's see, should be something like that. Roughly. Of course, it's an approximation. But the purple curve is what we should see if you plot that with Matlab. Does the phase make sense? Yeah. Any questions? No. Okay. Sure. No questions. All good. All right. So if I hear nothing, let's continue. The next question is calculate the phase, calculate the magnitude, phase and magnitude, I think at 10 to the power of 4 radians per second. According to our graph here, we should get something very close to 0 dBs and something very close to 0 degrees for the phase and magnitude. So let's try to do that and see what we have. To find the phase and magnitude, we simply replace S with J omega. And then we're going to find the real and imaginary components. So you have J omega plus 1 to the power of 3, J omega plus 0.1, J omega plus 10, and J omega plus 100. The magnitude of Gj omega is square root of imaginary part squared plus real part squared, all to the power of 3, because you have 3 of them. And then the magnitude of each pole, omega squared plus 0.1 squared, imaginary plus real, and imaginary plus real part squared. All right, so taking the magnitude of each individual pole and 0, that we calculate as the square root of the sum of the real part squared and the imaginary part squared. If you replace omega with 10 to the power of a -4, 10 to the power of 4, this gives approximately 1. Approximately 1. You were supposed to get 0. The J indicates what the imaginary part is, right? It's not part of the imaginary. If you do J omega squared, or everything, you get a negative omega squared, right? So J is only there to indicate what it's a vector, only the coordinate of that vector. So it doesn't go in the calculation of magnitude. So we got 1. We're supposed to get 0. Where is the mistake? Aha, it's 0 dB, and this is not dB. This is just the absolute magnitude. So to go from this to dB, we need to take 20 log of 1, which is 0 dB. Okay, so that matches what we measured before. Now let's see if the phase matches the Bode plot. What is the phase? Tell me the equation for the phase. The phase is this is the phase of all zeros minus the phase of all poles. What is the phase then? The phase of one individual pole or zero is the inverse tangent of the imaginary divided by the real part. What does that give us here? 3 times the inverse tangent of omega divided by 1, because you have 3 0 at that frequency, minus inverse tangent of all poles now, omega divided by 0.1, omega divided by 10, and omega divided by 100. If you do omega equals to 10 to the power of 4, we should see something around 0.6 degrees, which is close enough to 0.